English with Astronomy, Episode 8.
Yes, we've talked about our galaxy. Now let's learn about its most famous residents.
Excellent! We're talking about stars. The next episode is called What Makes a Star a Star? When we look at the night sky, all stars seem alike, small bright points twinkling in the dark. But if you look more closely, that first impression fades. Some stars shine more brightly than others. Some look bluish, others reddish or yellow. Behind these differences lies an amazing variety of worlds, each living by its own rules. What is a star? In essence, it is a gigantic, superheated ball of plasma with nuclear fusion raging in its core. In the center, where pressure and temperature reach extreme values, hydrogen nuclei fuse together and become helium. This process releases colossal energy, the very energy that makes a star shine. Nuclear fusion resists gravity and keeps the star from collapsing under its own weight. As long as there is fuel in the core, as long as the invisible balance between compression and radiation holds, the star stays stable and continues to shine. Our sun, for example, turns millions of tons of its mass into energy every second, and it has enough fuel left for billions of years. Stars differ first of all by color, and color is linked to temperature. The hottest stars blaze with blue or white light. Their surfaces heat up to tens of thousands of degrees. Such are the bright stars in Orion, Rigel and Bellatrix. They sparkle like icy diamonds, flaring with a cold fire. A bit cooler are white and yellowish stars, like our sun. At the other end of the scale are red giants and red dwarfs, relatively cool stars glowing with a dim crimson light. The famous Betelgeuse, also in Orion, is just such a red supergiant, with a surface temperature of only about 3,000 to 4,000 degrees. But temperature is only one side of stellar diversity. Stars also amaze us with their sizes. Some are true giants, hundreds of times larger than the sun. If such a star took the sun's place, its swollen outer layers would swallow the orbits of the nearest planets, Mercury, Venus, and possibly even Earth. These huge but fluffy balls are held together only by gravity, and their matter is no denser than Earth's atmosphere. At the opposite extreme are dwarf stars, whose sizes are comparable to planets. White dwarfs, for example, fit into a volume similar to Earth's, yet their mass is enormous. Their matter is squeezed to unimaginable densities. A teaspoon of it would weigh several tons. And neutron stars are even denser and more compact. They're heavier than the sun, even though their diameters are comparable to the size of a city. Most stars are not alone. They live in pairs, triples, or even in entire groups. Double stars orbit each other in a cosmic dance, bound by mutual gravity. Sometimes they're so close that they exchange matter. One star pulls streams of hot gas from the other, and this can continue for millions of years. There are also star clusters, hundreds or thousands of stars born at the same time from one cloud of gas and still traveling together. One of the best-known clusters is the Pleiades in Taurus. With the naked eye, you can see 6 or 7 little stars, though in reality, the cluster contains more than 1,000. Stars are not eternal. They are born, live, and die. Young, massive stars are hot, bright, and wasteful. They burn through their hydrogen quickly. The most massive giants live only a few million years, then explode as supernovae, throwing heavy elements into space, material that later forms new generations of stars and planets. Small stars, the modest red dwarfs, are the opposite, incredibly thrifty. They burn so slowly that they can exist for tens or even hundreds of billions of years, longer than the current age of the universe. So each star in the sky is not just a point of light, but a whole world with its own history, character, and fate. Together, they create a grand show playing out above our heads on every moonless night. Questions ready?
Questions and recap, both ready.
Go ahead.
First question. According to the text, what is a star and what process powers its light? Second, how does thermonuclear fusion prevent a star from collapsing under gravity? Third, what are white dwarfs and neutron stars? Fourth, how do the lifetimes of massive stars and red dwarfs differ? Now listen to my story about stars. What is a star? Think pressure cooker made of light. In the core, hydrogen fuses into helium, and that energy pushes outward just enough to balance gravity pulling in. That tug of war is why stars hold their shape and shine. Colors are thermometers. Blue-white stars, scorching. Yellow-white, like our sun, cooler. Red giants and red dwarfs, cooler still. Betelgeuse glows deep red, a swollen supergiant. Rigel and Bellatrix are blue-white torches. Sizes go from absurd to mind-bending. Supergiants balloon big enough to swallow the inner planet's orbits. White dwarfs are Earth-sized cinders with sun-like mass, gravity packed tight. Neutron stars shrink the drama even further, city-sized yet heavier than the sun. Most stars don't fly solo. Many live in pairs, orbiting each other, sometimes even trading gas like cosmic dance partners. And some are born in batches, open clusters such as the Pleiades, sibling stars from one cloud. Lifetimes, it's all about fuel burn. The big, bright ones live fast and die spectacularly, supernovas that forge and fling heavy elements into space. Thrifty red dwarfs sip their fuel and can glow for tens to hundreds of billions of years. So every point in the night sky isn't just a dot, it's a story. Put them together and you've got the grandest light show in the universe.
Great! Let's hurry to the third episode and then go outside to observe. The sky has cleared unexpectedly. Time to seize the moment.
Fantastic news! Let's go catch this opportunity and something beautiful in the night sky.
On to today's final episode.